Hello, grade 12s. I want to talk a little bit to you about some of the trends that we can find in the periodic table. We've discussed some common characteristics and trends before, but there's a lot more we can know about elements just from their position in the periodic table now that we have a better understanding of the structure of the atom. So when Mendeleev originally created the periodic table, he arranged things in order of atomic mass. He took a whole pile of cards of all the chemicals that we knew at that time and started rearranging them into groupings that had similar properties. And what he noticed is that once he had those similar properties, they tended to repeat about every seventh element if you put them into rows of 7. Now, the reason he did 7 rows instead of 8 is because we hadn't discovered the noble gases at that time, because we were learning about elements in terms of how they react. And of course, the noble gases are non-reactive. So he found out that by arranging them according to atomic mass, there was a periodic reoccurrence. So in 1913, Henry Moseley made a slight adjustment and found that we actually get better groupings of properties if we arrange them by atomic number rather than by atomic mass, and that made a couple of small changes to the periodic table as we know it. But for the most part, it is the same. So one of the things that Mendeleev wouldn't have had any idea about was electron configurations. This would not have even been something that would have occurred to him because he didn't know about electrons. It wasn't discovered at that time. And yet what we have found when we've done our electron configurations and our orbital diagrams is that the position of an element on the periodic table actually tells us not only the energy level that its electrons will be found in, but even more, it tells us the sub-level that they can be found in. Another interesting thing that we can see when we're talking about periodic trends is atom size, the size of the atoms. Now, for the most part, as we go down each period and as we move down, most of us understand that atoms get bigger. If I take a look at, for example, lithium. Lithium, when we would draw it, if I was to draw it like a Bohr structure, would have 2 rings because it's in the second period. Lithium, we would find sodium, and sodium would have 3 rings. Below sodium, there'd be potassium with 4 rings. So of course, we're getting bigger because there's an increased number of rings. And most of us have no problems with that concept. The question is, in which way what happens when we're working across the period? So suppose I'm interested in what's going to be happening if I want to compare sodium and then start moving across to magnesium, and end up moving all the way across to even chlorine. What happens in a case like this? Well, lots of times I get kids thinking they must be getting bigger as we move across because, of course, we're adding more electrons, but actually the opposite is true. If we compare sodium to chlorine, and we could even go one over to argon, but I'm not going to talk about the non-reactive gases right now, although the trend will continue. Sodium, when I have a sodium atom, has 2 rings of electrons. Or 3 rings of electrons, sorry, it's in the third period. Chlorine also, when I draw a chlorine, has 3 rings of electrons, if we're thinking about a good Bohr diagram. The difference between sodium and chlorine is what is holding those electrons around as they spin around the nucleus. In the case of sodium, there is 11 protons pulling those electrons in towards it. In the case of chlorine, there are 17 protons pulling. Now, 17 is a lot stronger than 11 is. So what that means is that chlorine can actually take and pull its rings of electrons a little closer into its nucleus. It's a stronger element in terms of its strength of its nucleus. So what I need us to understand is that as we go down, we get bigger, and as we move to the left, we get bigger. So francium, down in this bottom corner, is the biggest element that we find on the periodic table, and fluorine will be the smallest. Now, of course, helium is smaller than chlorine, but again, I'm going to leave the non-reactive elements out for the purpose of our discussion today. So I want to relate everything we do now to size, and everything's going to come down to what I call those two effing elements, francium and fluorine, which sounds kind of funny, but it's a good way to remember it. If we can remember that our biggest atom is down in this corner and our smallest is up in this corner, I can relate all of the other periodic properties according to the size of the atom. Let's start with ionization energy. Ionization energy talks about how much energy it takes to remove an electron from a gaseous atom. So if I have an atom and there's a nucleus, and that atom has rings of electrons going around it, and there are electrons floating in the ring. What's holding the electron on is its attraction to the nucleus. So the stronger it's attracted to the nucleus, the more energy it would take to shoot that electron off and free it. The smaller the atom, the stronger the electron is attracted, the more energy that is required. Think about holding a basketball in your hand. In one case, you hold the basketball very close to your head. In another case, you stretch your arm out far and hold the basketball very far away. Where is it easier for somebody to knock that basketball out of your hand? Well, of course, the bigger you are, the easier it is. So it's a very similar concept. The smallest atoms have the highest ionization energy. So when we come to this upper corner with the smallest atoms, this is where we're going to have very high ionization energies. I sub E. The biggest atoms have the lowest ionization energies. Okay, so the smaller they are, the harder it is to remove. The bigger they are, the easier it is to remove. We can remove more than just the first electron, though. It was really interesting because this is how we actually managed to figure out the structure of an atom in its first place. We were taking a look at how much energy it takes to knock off each successive electron as we go. I always like picturing Marvin the Martian as my little idea of what ionization energy might look like. Suppose Marvin had his little ray gun and was shooting off the electrons one at a time. We would see that the outermost electrons were the easiest to knock off. So if he shot his little ray gun and managed to hit an electron and knock it free, he could have a little meter on the side and he could measure how much energy it took to knock that electron off. What he'd find is that the first electron came off very easily. The second electron would take just slightly more energy to remove. So when he goes to shoot off the second electron and knock it free, it took just slightly more energy on his ion gun to remove. And so electron 2 is now removed. At this point, we would imagine that both of these electrons are gone and the next ring is now full. A full ring is a stable ring. So when Marvin goes to shoot off the next electron, what we notice is that there is a very large jump in the amount of energy. This big jump in the amount of energy tells us that we are starting to disrupt an already stable ring. Each of the next 7 electrons, so as we go through a series of 8, again, has slightly more than the one before because, of course, the same amount of protons that we have in this nucleus are pulling on less and less electrons, and so they're holding them tighter. This will continue to happen until we've knocked off all 8 electrons in this ring. And if he keeps turning the energy up on his gun, what we notice is that we're going to have another big jump as we go to the next stable ring. And the very last ring has only 2 electrons in it. So this was my innermost ring, the one that was the most difficult to remove. And this was my valence ring. Suppose that I looked and I said that it took a low amount of energy to remove 1 electron, and then another low amount of energy, and then all of a sudden I saw a high amount of energy. The fact that there was 2 low energies and then a high tells me that I would have 2 valence electrons. If I said low, 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 high, I have 3 lows. This would be an indicator that I had 3 valence electrons. So valence electrons are easily removed. The next trend I want to talk about is electron affinity. Electron affinity talks about how the energy in an atom changes when we add an electron. If an electron gets more stable, then we say it has high electron affinity. So electron affinity talks about how much more stable it is. Is it happier, if I could use that term, when we give it an electron? And atoms who are happier are ones who are almost full in their rings as it is. So there are some ups and downs here, but the general rule is the smallest atoms have the highest electron affinities. The largest atoms have the lowest electron affinities. So in general, as we get smaller, the electron affinity will increase. We can also find out about atoms and ions. Now, if I'm comparing one ion to another, for example, lithium to sodium to potassium, as we go down this row, as we go period by period, what we start to notice is that the ions get larger. And for the exact same reason that atoms got larger, we're adding more rings. Okay, we notice that even with fluorine, chlorine, bromine, as we go down, we get larger. So the one thing, if I'm comparing one ion to another one, I can use the same reasoning that I used for atoms, and the bigger we are, the closer we are to francium, the smallest ions are the ones closest to fluorine. But there's also a comparison between the ion and their corresponding atom. And the general rule is when we form a cation, for example, lithium turns into lithium ion, we get smaller. And we get smaller because we've removed a ring. Remember, if we think about lithium, there are 2 rings of electrons. And what I've done is I've removed that outer ring, so of course it's smaller. So as we form a cation, we become smaller. As you form an anion, you actually become bigger. Now, you're not becoming bigger because you're adding more rings, but you're becoming bigger because you're causing the electrons in that outermost ring to have to spread apart a little bit. Consider for a minute that chlorine atom wants to become chloride ion. We can see that there are 7 electrons in its valence ring. So this would be the 3rd ring out, its outermost ring, its valence ring. In order to add another electron, we will have to cause all the rest of these to spread apart. Everybody's going to have to back up a little bit and space out because right now they're too close together. So as we spread all of the existing electrons out, we make room for the 8th. And you can see that we've become larger than we were in the atom. So as we go from chlorine as an atom with no charge to chloride as an atom with a 1- charge, we've added an electron, we have become larger. Electronegativity is another trend that is readily associated with an atom's position on the periodic table. Electronegativity talks about how strong an atom is at attracting not only its electrons, but the electrons of neighboring atoms. There are 2 things that we need to consider with electronegativity. One thing we need to do is consider the size of the nucleus compared to the amount of rings. We call this effective nuclear charge. Another thing we consider is the amount of rings of electrons that might be surrounding that nucleus and therefore shielding that positive pull from the nucleus from other atoms. This is called electron shielding. So again, the general rule of thumb is the smaller the atom, the greater the electronegativity. Fluorine is the most electronegative element on the entire periodic table. Not only does it hold strongly onto its own electrons, but it also pulls very hard on the electrons of neighboring atoms. Francium can barely hold onto its own electron, never mind try to attract electrons from another atom. Although it has a very large nucleus with 87 protons, because it has 7 rings of electrons, a neighboring atom can barely, if I could use air quotes, see the electrons or the protons in the nucleus, and therefore there's so much electron shielding that you cannot have a very high electronegativity. Electronegativity relates to the reactivity of elements as well. Metals and nonmetals react differently. Metals react by losing electrons. So an atom with a low electronegativity will lose its electrons readily and be very reactive. Nonmetals react by gaining electrons. So in the case of a nonmetal, high electronegativity is very reactive. When I ask you which of two elements is more reactive, you must first decide if it's a metal or a nonmetal. We can do this by finding the zigzag line on the periodic table. Everything to the left of the zigzag line is a metal, and the most reactive of our metals is francium. If you are comparing nonmetals, nonmetals are found on the right of the zigzag line, and the most reactive of my nonmetals is fluorine. I recommend you create a quick summary of your periodic trends for yourself in your notes. You can practice what we've learned about periodic trends from your readings in Chapter 6 and the questions you find on page 199. Also, in your work package, there is a worksheet with 8 questions on it called Worksheet on Periodic Trends. Do this worksheet because it is the form that I will test you on when I test your understanding of periodic trends at a later date.